Okay, in this video, we're going to talk about reaction mechanisms, which you'll find is really similar to Hess's law. So what we say, remember when we are, let me think about how I want to start this. Remember how we are writing the rate law expression where rate is equal to K times the concentration of reactants raised to whatever order they are, and their order is how their change in concentration affects the rate. And I give you the reaction, but the coefficients in the reaction mean nothing for the order. The order has to be experimentally determined. Well, we're going to figure out exactly where that order comes from. Like, why are some reactants second order? Why are some first order? Why are some zero order? So many reactions actually occur in steps, like little mini reactions, where the overall reaction is the sum of the steps. And each step that's in the reaction has a different rate. Some are slower than others. So imagine you're getting ready for school in the morning. You get up, you get dressed, you brush your teeth, you have breakfast, and you drive to school. That's the same routine Mr. Tyson has. Now, Mr. Tyson is driving all the way in from Howell. So if you think about his, all of his steps of waking up, getting dressed, brushing his teeth, the longest step is his drive. So if he was going to try to somehow find a way to speed up his morning routine and get to work faster, he'll get the biggest bang for his buck if he takes a helicopter to work, right? That slow step is what really determines how long it takes for him to get to work. So that's why the slowest step in a mechanism is called the rate determining step. It has the most effect on the overall rate of reaction. So sometimes we call this RDS, rate determining step. That's the slowest step. This is the step that determines the rate law of the reaction. We'll see that the coefficients of this step are actually where the orders come from. So let's do an example. So these are the steps of an overall reaction. What is the overall reaction? Well, we're just going to add up these reactions just like we did in Hess's law. So if you see a compound on the left and the same as the right, they're going to cancel. So, for example, if I use up one of these NO2s, but I make another, basically cancels. One on the left, one on the right. Same thing with the NO3s. So when I add these reactions up, I get NO2 plus CO makes NO plus CO2. That's going to be my overall reaction. Now, looking at the steps, what is our rate determining step? It's our slow step. So that really determines the rate of this overall reaction. Now, the coefficients in that step is what determines the orders of those reactants. So this is when we actually can look at coefficients. It's only when we look at the coefficients of the rate determining step that is what helps us determine the rate law of the overall reaction. So if I were to look at the rate law for the rate determining step, I can actually use the coefficients. So I have the concentration of NO2, but I have two of them. So that'd be like two sets of NO2. The coefficient will be 2. That means the order of NO2 is 2. It's second order. Now notice that CO is a reactant in the overall reaction, but it's not a reactant in the rate determining step. So think about what order might that be if the concentration of CO, if the CO isn't in the rate determining step. That tells you that it has to be zero order. Its concentration has no effect on the overall rate of reaction. A couple other things to note. If you notice, some chemicals show up in the steps, but they're not in the overall reaction. So when you have a chemical that shows up in the steps, but not the overall reaction, it could either be a catalyst or an intermediate. NO3 is an example of an intermediate. An intermediate is something that is made and then used up. So it's a chemical that is made or produced, then used up. So you're going to see it show up on the product side first and then the reactant side. Now, a catalyst is the opposite of that. A catalyst is something that is used up and then reproduced. Now, we should all know that catalysts speed up reactions. So that means it must be part of the rate determining step. It's used up in the slow step and then reproduced later. So that's how you might actually see a catalyst show up in the rate law expression, even though it's not in the overall reaction. So we'll get to an example of that soon. All right, so let's determine the overall reaction and its rate law. So maybe pause the video, see if you can add these up and get the overall reaction and possibly the rate law, determine any catalysts or intermediates. All right, here we go. I noticed that I have iodide on the left side and on the right side. So I know that those are going to cancel out when I add up these reactions. I also noticed that I have IO minus on the right and I have IO minus on the left. So those will cancel as well. Now 2 sets of hydrogen peroxide will give me 2 sets of H2O2. That'll make 2 waters and an oxygen. So this is going to be my overall reaction. My rate determining step is the slow step. The rate law is based off of the coefficients of that rate determining step. So the rate is going to be equal to the concentration of hydrogen peroxide, and because there's 1 out in front, that means it's first order, times the concentration of iodide ions, and because there's an imaginary 1 out in front, it's also raised to the first order. So this is going to be the rate law expression of the overall reaction. It's based off of the coefficients of our rate determining step. Now, if you notice, the iodide ion affects how quickly the reaction takes place, right? If we double the concentration of iodide, we're going to double the rate. However, that is not part of the overall reaction. So something that affects the rate but doesn't show up in the overall reaction, can you think of what that is? It's a catalyst. I minus is a catalyst, right? We use it up in the rate determining step and it's reproduced later. So remember, we say catalysts are not really part of the reaction. Well, they're not part of the overall reaction. They're part of the steps though, because we use it up, but then we remake it. Do you see any intermediates? It would be IO minus. That would be an intermediate. It is a chemical that we first have to make, and then it gets used up later. Okay, this concludes the reaction mechanism notes. There's not much to it. So if you're in my class, make sure you do that little mini assessment, just so I understand, make sure you guys know what's going on here.